And then start. Okay. Welcome to the DDPS seminar, everyone. Before we introduce our invited speaker, let's go over some rules and logistics. First of all, please mute yourself during the talk. But if you have a question, you can unmute and ask question during the talk. Or you can use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audiences. Therefore, no classified discussion is allowed. And finally, the talk today will be recorded and uploaded in our YouTube channel. That's it. Let me briefly introduce our speaker today. It's an honor to host Dr. Eleni Chetzi, who is an associate professor and chair of structural mechanics and monitoring at the Department of Civil and Environmental and Geomatic Engineering at ETH Zurich. Her research interests include the fields of structural health monitoring and structural dynamics and intelligent data-driven assessment of engineered systems. Today, Eleni will present an exciting topic, which is twinning and model discovery for engineered systems. I'm sure we will hear an exciting talk today. But before I pass the baton to Eleni, let me ask a couple of questions just to get to know you better, Eleni, and make this seminar somewhat informal. All right, are you ready?
Yes, go ahead.
All right, the first question is, obviously, you are passionate about structural health monitoring and structural dynamics in general. Is there any moment in your life when you realize that, wow, this is it? This is the field. I would like to commit my career onto this field. Do you have that moment?
A moment of realization. It's a good question. I should explain, monitoring for me was something new to discover when I came to the US, to Columbia University to work at the civil engineering and engineering mechanics department on this theme. Until then, I followed the more traditional civil engineering studies that were not so much into the concept of data, system identification, exploitation of such technologies, let's say, at that point in time. And so it was already something new and exciting, which sparked my interest from the beginning of my doctoral studies. But I think the realization came near the third year of my studies when I actually got to go on the Manhattan Bridge, which is an iconic structure in New York, and deploy sensors, sensing instruments ourselves, together with a group of my advisor at the time, Professor Andrew Smith, and actually, gather the data that was to be used for something practical, for something that I could see a tangible outcome. And at that point, I realized, okay, this is something I would like to do. And it's not just about maybe theory, which is on its own exciting, but it's possibly something that could help me effectively make a difference, or, at least see it applied in a way that makes sense. And I think that's what made me more excited. And that's when I decided to get into this in a bit more serious or academic, I guess, manner.
Very nice. So you do have that moment.
I feel like this was it for me. That's true. But you can never be completely sure. I think many things form the culmination or the accumulation of several smaller experiences that somehow add up to something. But maybe the realization, could be pinned down to a moment, I suppose.
I see. All right. The second question, which is the last question. You are now serving as Vice President of the European Academy of Wind Energy. That's such a big job, sounds like. How did it happen? Would you mind sharing a brief story about it?
Yes, so maybe this is closely related to what the experience I described before. So for me, applications in wind engineering came rather, it's not that recently, but I think it was not until 2015, actually, or 14 rather, on the occasion of a grant that I was writing that is equivalent to a career grant in the US. It's an ERC starting grant in Europe. Where the idea was to suggest a topic that was new and bold, something that hasn't really been tried before. And at the time, the structural monitoring of wind energy structures was not really something that was heavily pursued. Not much work existed from the point of view of methods that exploited structural monitoring data, structural mechanics models in tandem with data. And so through the approval of that grant, I began to become, I sort of entered this realm of wind energy structures, which was again new to me at the time, but I also came slowly to know different colleagues, to work more closely with colleagues in Europe, and eventually entered this European Academy of Wind Energy, where many of the colleagues that work in the wind energy domain participate to represent their institutions. And that's how I became a member of that society, and now I'm the vice president of the society at the moment, representing the field of structural monitoring and representing it in actually a field that is in itself very, very broad. So we have colleagues from the domains of control, power grids, electrical engineering, civil, more traditional or structural analysis groups, and of course, fluid simulation. So it's really a very diverse field that has to somehow work in tandem for a common goal, which is actually the resilience and the performance design of these systems and structures. So again,
Awesome.
something new and exciting for me. Not so new maybe anymore, but certainly remains exciting through the interdisciplinarity of the topic. So I'm
Yeah.
glad to be part of this society.
Awesome, awesome. Well, you know, the excitement followed some responsibility, I guess. So,
Yes, but it's this is true, especially when these societies are as diverse. But it's also a pleasure to work with colleagues from all these different origins and I guess skills and interests.
awesome, awesome. All right, I will not bother you with any more questions. So the floor is yours. You can share your slide and then just
Yes,
fly from there. Yeah,
let me try that. I think you mentioned that we could also take questions during, so that's also welcomed for me.
awesome.
And I'm going to try and give a small overview here of the work that we do in my group, the Chair of Structural Mechanics and Monitoring at ETH Zurich, on this theme, the theme of twinning and model discovery for engineered systems. And you already see a wind turbine there because it has become, or it has grown to become, a substantial portion of what we deal with. But the truth is that our applications span along a rather broad domain of applications, with the golden thread being this concept of structural health monitoring, which your first question allowed me to elaborate on. And structural health monitoring, from my point of view, can only be conceptualized as a chain which initiates with the gathering and accumulation of data from different types of sensing sources, offering heterogeneous information of diverse types. In my group, we're particularly interested in exploiting vibration-based signals because often they are very rich in content and information. And that's also why we, in the chair of structural mechanics and monitoring, one of the domains of our expertise is also structural dynamics. And what we try to do on the basis of this accumulated data is to exploit the information and translate it into something that is interpretable, something that can be used by engineers for their management, for the management of their assets, typically in two configurations: the diagnostic configuration, where we try to assess the condition of the system as is, and the prognostic configuration, where we're interested to learn more, or predict rather, the future performance or remaining useful life of a system, extracting quantifiable indicators that can guide us to their operation, maintenance, and overall management. Now, of course, the translation of data into something that is meaningful information is not trivial, and this is where the strength of what we develop comes in, or at least the particular expertise of my group, which lies in the exploitation of models that draw from principles of physics. Physics represented in the sense of mechanics or dynamics, and where through these models we can actually maximize the information that can be drawn from the raw data. And after creating this kind of a synergy and creating these quantifiable metrics of system performance, we try to then extend these to the system level. So I spoke earlier of wind turbines, but we're also interested in trying to understand performance at the level of the farm, or the fleet of farms that are operating or on which we draw data from. Or if we're talking about more conventional civil engineering infrastructure, we would be talking not only about individual bridges or road components, but rather of the transport network as a whole, as an entity that can be managed on the basis of flow of data. So these are the elements of the chain that make up SHM, but also the chain that is relevant for us in terms of the fields that we're active in. So as I mentioned before, we gather data from various systems. We have a collaboration with the railway authorities here in Zurich, where we use sensors mounted on trains or vehicles to understand the performance not only on the vehicle fleet side, but also the traversed infrastructure side. We deal with more traditional civil engineering applications like the monitoring of buildings under, for example, seismic excitations, or the monitoring of bridges under the different types of loads that they are exposed to, including aging and slow evolving deterioration forcings. And of course, talking about condition monitoring, we also have applications in the more traditional area of industrial assets, and of course, wind energy structures. In fact, it might be interesting to know that we even own a turbine. So this is a turbine that is not too far from our campus, in which we use as a living lab. It's sort of a toy in a sense that we try to use and experiment with for testing and verifying our methodologies. And so I will focus in this talk, as the title somehow hints, on the aspect of modeling or the inference of models and how this can be used in a way that makes sense or maximizes our understanding of a system, which is what we would like to do at the end of the day. But before I do that, I always think it interesting to also point out what we can do on the basis of pure exploitation of data without necessarily trying to include some knowledge of the physics that underpins our problem. And to do this, I will show you again an interesting application here at the farm actually level from wind energy monitoring. So in this case, we're trying to see if we can produce a data-driven model that can capture the effect of wakes, which is actually the effect that these front turbines will have. And you see it here, this shadow that is created on the basis of how the wind is oriented within a site, which has implications for the downstream turbines, not only in terms of the power that they produce, but also in terms of the loads that they experience, and therefore the fatiguing of these turbines and eventually even their condition through the accumulation of such wake effects. Now, if you would like to model this with physics, the problem could become quite complicated, and there are models that try to approximate the problem, but of course there's no guarantee that they reflect exactly what is the condition on site. So to tackle this issue, we actually use the data that we monitor, that we draw from monitoring of these turbines, so data at the level of the hub that give us information about the mean wind speed and orientation, as well as the power production, but also moment data that has to do with the loads that are experienced by these turbines. And we try to develop a data-driven model in this case, which admits as an input the mean wind field conditions as you would gather them from a meteorological mast, and translate them into what is the prediction of the wind that will affect the individual turbines, and by extension, what are actually engineering critical quantities like the wind deficit that would be experienced by these turbines, depending on the orientation of this mean wind. And the way in which we did that here has no physics, actually. It draws from the learning on the rich collected data over a large period of time. And we use conditional variational autoencoders to create this generative model. And the conditioning was, of course, done on these mean wind conditions, which is essentially what defines the output and the prediction of these models. So this is nice because this is something that reflects the reality. It's still a model, it's still a generated model, but of course, we didn't have to use any complex physics-based information that could probably also take a long time to compute. At the same time, it gives us information on critical quantities. In this case, we can also compute damage equivalent loads, which from the engineering perspective is important for judging as to the operation of these systems. But the issue is we cannot always get away with neglecting physics. And it's great when we have these loads of data, at least of that form, as I showed you for turbines, the SCADA information that ensure this knowledge on wind conditions. But there exist quantities that are not so easy to infer or to understand just by straightforwardly looking at the raw data. One such aspect is the dynamics that may be underlying the system, and this is something we're interested to know because it could actually define its performance. And so, as I mentioned before, we typically are in the business of collecting dynamics data or vibration-based data, usually by mounting acceleration or strain gauge type of sensors. Here you see an installation. Okay, it's a graphic, but it's a typical installation we also have on real systems. An array of sensors, for example, on a tower of a wind turbine, from which vibration response would be collected. And here, what we would like to do as an interim stage, where we try to bias a bit on the knowledge of, the dynamics that is governing the system, we try to represent this by using appropriate time series-based representations. Again, they are data-driven, but within them, they carry the structure of the expected dynamics. I will describe a bit on this in what follows. So in this case, we try to describe our dynamics with parameterized models, and at the same time, we know that the performance of a system over the long period of time is dependent on the influencing environmental and operational variables. Again, the mean wind field direction or speed, which could change over time. It could be the temperature and humidity conditions, the wave loadings that are seasonal. And so in order to have a holistic model that can capture the condition, or rather the response of the system over an extended period of time, we try to build these dependence models, which are really bi-component models. One part to take on the response of the system that is measured in the short time, and a dependence model to take on the influence of external agents or these environmental and operational variables onto the response of the system. There are many ways to achieve this dependence, and I am listing here only some of these, at least the ones that we have worked with. But at the end of the day, what is important is that we can manage to construct hierarchical models, which are predicted models of the quantities that we measure, and which we can then use as a means to create condition assessors of the system that can then signal as to possible damage. Now, I want to say here why I mentioned before that these data-driven models that are time history, essentially time series type of models, actually encode within them some of the dynamics of the system. And this is because if we have a nonlinear system, we know that we could approximate it by using compact parametric representations of the autoregressive type, which are particularly suited for nonlinear models. This would be the nonlinear autoregressive class of models, which you see listed here. And similarly, for non-stationary systems, we could have corresponding parametric representations like a discrete wavelet transform, or for time-varying systems, which is really what our wind turbines are, we could use a time-varying autoregressive class of models to encode the dynamics that we expect in the model that we try to use to approximate the system. And this is quite convenient because when you want to have a holistic representation and a dependence on influencing agents, a parametric model gives a natural means to do so, because these coefficients or parameters of the model can be conditioned on these influencing agents. And this is one way to do this. Actually, the expression that you see here is through a polynomial chaos expansion. It's basically an input-output surrogate, stochastic surrogate, which gives the dependence of these coefficients as the environment changes. Here's a practical example of this on real measurements. So this is an acceleration time history from a tower of a wind turbine, one of the turbines that we monitor. The specific one is in Germany, actually. And here you see the spectrogram that would correspond to this plot in the contour. Now, in the spectrogram, through the intensity of the colors, it is clear that the frequencies of this dynamic system are not constant. So we're not talking here about a stationary system, a system which under traditional system identification tools would be easy to understand through what we call operational model analysis methods, but rather a system that is time varying, and where a time varying model, such as a time varying autoregressive model, as I mentioned before, could be used to track the evolution of the dynamics. And this is what we did here. This is what you see superimposed through these blue curves that are really able to track the evolution of the dynamics in this short time, 10-minute window. Now, the problem when we collect our data is that, of course, if I look at another 10-minute window with another mean speed of the wind or mean orientation of the wind, this portrait would likely change. It would change because it's conditioned to these external agents. And this is actually something that we can take on through the dependent structure. So a Gaussian process or a polynomial chaos expansion, or even a neural network model could be used to express this dependence and reflect the evolution of the dynamics over a longer period of time. For example, here you see the modulation over a period of a month. The conditioning is done on data that is collected, and that's the nice thing about wind energy, wind turbine structures, that we traditionally collect this supervisory control and data acquisition SCADA information, which give us a 10-minute average data on wind direction, speed, power, temperature, and many more parameters. And this is what we condition on. And if we can do that, then we can train for a sufficient period of time our hierarchical model and then use it as a predictor and understand the deviation between what we predict and what it is we measure. Of course, there will be outliers which have to admit the robust outlier analysis and statistical analysis so that we can then classify the alarms that we receive, or rather the indicators that we calculate as in the green region. So operating as expected in normal conditions. In the red region, so in known environmental conditions, we receive alarms. So this means we have to act, or we have to signal for repair or intervention on our system. Or we receive alarms which are actually outside of the regular thresholds of our environmental, let's say, conditions. And this is what we would issue as an orange alarm, which means that there's something off, but it could be off because we are in a new environment. And this is something we have to treat with further analysis. So in structural health monitoring, because we're in close collaboration often with operators and engineers, we like to present these red, amber, green type of alarms to the let's say, the stakeholders. And this is something that they're more comfortable with, that they understand, more so than just a plot with outliers, let's say. And one step further, we can even help them to localize damage up to a degree. For example, this is something that we have done on a bridge structure, which you see here. It's a bridge in Switzerland, which we controllably damaged with different scenarios that we inflicted ourselves so that we can know where damage is located at. And we showed that by using a network of sensors now, not looking at individual sensors, but at the changes with respect to how the sensors are placed, it is possible to a degree to also localize perhaps the damage. And of course, this will depend on the density of the sensor network and a few more configurational aspects. But what it tells us is that we are quite successful up to this point in diagnosing damage, understanding if it exists and maybe where it is. But if we just want to stick to the data, we cannot do more than that. So we cannot prognose what happens next or how longer our system can go for without actually experiencing a critical failure. So the moment we want to go a step further, we maintain that data on its own is actually not enough. And this is the point where in our analysis, it is important to bring in an engineering model, a model that goes beyond the purely data-driven representation and the diagnostic capabilities, but brings in the physics that can help us, in a sense, extrapolate or understand how the system can perform, all the while being updated by the data, reflecting our system as is. So this kind of a concept of merging physics and engineering, intuition and models with data is the hybrid approach to modeling, is what allows us to go to produce these so-called twins that are actually interactive, that somehow close the loop of communication between the actual physical system and the virtual mirror or the virtual instance that we are creating, since there is always this communication flow that is ensured by the data. Precisely because this interaction is important, in our group we pay particular attention to models that can compute fast, compute ideally in real time, so that we can ensure that we have a connection between the two systems, the digital and the physical system, always and without interruption. But to do this, we have to ensure that the computational toll of our models has to be low, a task which is actually non-trivial. and on which I would like to actually focus on. So let me actually go directly here. How we can fuse data and physics-based models for learning, monitoring, and twinning, and feasibly do so in real time. Now, the reason why this is not an easy task is not only because of the complexity of the models, which is often what causes them to be slow in terms of computation, but it's also because the effects that we have to account for are rather complex. I already referred to the aspect of loads that reflect varying environmental and operational conditions. This could also refer to loads that lead our systems to experience nonlinear behavior that is beyond the easy to compute, let's say, linear elastic range. In fact, most of our loadings are distributed loadings, so it's not easy to model these with just simplified point sources. And further to this, they're also in most of the cases actually unknown or even unmeasured. And so we have to deal with all of these intricacies and try to deliver a predictive model that can cope with this uncertainty and do so in real time. And the motivation being that we would like to use this as explained before for twinning applications, for the goal of virtual sensing. Virtual sensing is the situation where we wish to extract information from a system, predictive information beyond the usually few and sparse locations where we sense. And when we try to construct a proper digital twin, this is very, very important because we should not just be predicting where we measure, but rather in the full field of this object that we try to monitor. And of course, the downstream tasks are numerous, including control and diagnostic aspects that have to do with maintenance. So I will pick one of these tasks to exemplify the framework that we have set up. And for me, the most interesting, as I sort of hinted, is the aspect of virtual sensing. Predict the response of the system feasibly in real time in locations that are not measured, or as I come to refer to it, basically achieving everything everywhere all at once. And here's what I mean by this. This is our typical monitoring problem where we have a structural system on which some sensors, usually few and sparse, are located on. This gives us some sort of measurement information. Our system is operating under inputs that we cannot measure. That's the case for a bridge. Even for a wind turbine, we claim to know the wind speed and direction, but we don't really know the proper distributed force of the wind or the wave as it is acting on our offshore structure. We have, as engineers, some sort of a priori model that was used to put the system in place, but usually it's not an accurate model, or at least it's not a model that has been updated necessarily to reflect the system at its current point in time. And therefore, it could feature unknown parameters additional to model form uncertainty. And the objective is to extract the response of the system. These so-called unknown states is the response of the system in unmeasured locations, which actually can be numerous. So we would like to do all of this, learn the system, predict its response, so everything. And we would like to do it everywhere in the full field of the system. And we would like to do it in real time, which is basically all at once, given all of the challenges that I mentioned earlier. So here is how we try to approach the problem for doing so. First of all, we have to reduce the computation of our engineering models which we wish to bring in the loop. And in our group, we're a structural mechanics group, so we have had exposure to, and we helped in development of numerous methods on the more traditional front for accelerating computation from the point of view of fracture plasticity, geometric nonlinearity, or multi-structure complex assemblies. But not the majority of these methods just does not make the cut when we try to use them as is. We need to boost this kind of a computation, and one way to do this, and which is quite popular in recent years, is to do it through exploitation of the power of learning through machine or deep learning formulations. All the while, though, respecting the fact that we have to learn from physics and engineering intuition. So here's one approach to doing this. This is work by Tom Simpson, one of the PhD candidates who recently graduated from our group, who tried to reduce full order complex finite element models. So for civil engineering, this is one of the favorite types of models, usually with a large number of degrees of freedom, which compute in terms of dynamics, most often quite slow. And so what we did was to train on several instances of such models, or at least on several forcings that are applied onto such models to extract a so-called latent representation of this multi-degree of freedom system, essentially a reduced order space where the dynamics of the problem lives in and can be characterized, but with a condensed representation. And then we try to apply the forcing, the actual forcing of the system onto this reduced representation. And we used a numerical integrator, or the equivalent of this for neural networks, which is in our case, an LSTM, RNN type of model that takes our prediction from point time tk to the next point in time. So now we have computation on reduced coordinates, and we have a possibility to simulate the system in this reduced space over time. At the same time, through the nice property of autoencoders, we can go back to our original representation, the original finite element model, through the decoding step, and extract the response of our desired system in the full field, in terms of strains or accelerations, in general, in terms of the quantities that we're actually going to measure eventually from this system, simply through this decoding procedure. So this gives us significant acceleration. It allowed us to simulate systems that are nonlinear. So this one is actually a nonlinear benchmark that was defined by our colleagues in Los Alamos in the US, a nonlinear frame with a bumper where the response of the system is challenging to simulate with traditional system identification tools that prefer linear systems. So here we simulated the system using this autoencoder logic, showing that the reduced space that we extract from the system is actually a type of nonlinear normal mode. So they're basically modes that are independent. The majority of the spectral content of these modes reflects a specific actually frequency. They're still nonlinear representations, but it's actually what empowers us to then simulate the system using this reduced representation, even at the nonlinear case. From a practical viewpoint, we implemented this logic on the nonlinear response of monopile wind turbines, where nonlinearity comes from the behavior of the soil, where you see these typical PY curves on the basis of which the wind engineers will simulate these models. And that's indeed what our colleagues in Siemens Gamesa did. They did the actual simulations on which we trained this autoencoder type of reduced order model, which then replaced their simulation with high accuracy, only it did so in fragments of a second, meaning it gave us a computational model which can compute in real time and can be later combined with data, which is really what we seek to do. A bit of an issue in this reduction approach is that for most of these configurations, we haven't so far discussed the issue of simulating systems of different parameters. So even in this monopile structure, it's actually a fixed structure and system, but which we simulate under different types of loads, and we try to accelerate the simulation for this particular instance. But if you want to have a general model that can compute over different parameters and different configurations, so different shapes of the tower or lengths of the blades and whatnot, we have to construct a so-called parametric surrogate. And to do this, one of the approaches that we follow is the so-called projection-based parametric reduction. And I'm going to exemplify this on a benchmark that we tried to put out for the community. It should be that this QR code hopefully still works. This would take you to the page where this benchmark is defined. Of course, we're in civil engineering, so our benchmark is a common civil structure. It's a frame, which, however, features nonlinear joints. So each one of these links are described by a hysteretic model. It's actually a book-when type of model, which means that the response of the system to earthquake loading, which is a typical excitation for the analysis of these structures, is nonlinear. And what we would like to do here is to produce a parametric model, so a reduced order model that can run for different configurations of the system, meaning for different properties of the hysteretic model of these nonlinear joints, but also for different characteristics of the input forcing, the earthquake, which can come at different amplitudes and with different spectral contents. So To try and do this, the first thing we have to do is to actually parameterize our input, because we need also the input to be something that can form a part of our defining parameters of our model. And it turns out that for earthquake sequences, it is possible to actually parameterize these, and this was shown in the work of Rezan and Derkuregian. And we followed that work and essentially took real instances of earthquakes from the Peer Strong Motion database, where more than 2,000 actual earthquake time sequences have been recorded, and we broke them down into parameters that essentially have to do with the spectral and temporal characteristics of the earthquake, how the amplitude evolves over time, and what is the spectral content of the earthquake sequence. And by breaking them down into these parameters, we can actually now take a specific earthquake time series represented with these parameters that now form part of the definition of our problem. But perhaps the more difficult aspect here is to see how to reduce the nonlinear system itself. So, okay, we parameterize the input, the load, but we also wish to execute our simulation for different characteristics of our frame, maybe different elastic characteristics, but also hysteretic properties. And so to do this in affordable computational time, we follow a projection-based approach, where the original nonlinear dynamic equation of the problem, which is an ordinary differential equation, is brought down into a much smaller dimension, a dimension R that is affordable to compute. And the key to doing this is to construct or to multiply our original equation with this reduction basis, which is basically a Galerkin projection basis. All this is, in simple words, is basically a matrix that we assemble by having several simulations, we call them snapshots, of the original full order model. And by executing a singular value decomposition on those several time series, it is possible to extract this Galerkin projection basis, essentially a matrix, again, of main modes that govern the response of the nonlinear system. And by pre and post multiplying with this matrix, we end up in this reduced, still nonlinear equation, which is also parametric, has a parametric dependence. Now, what this means is, because the parametric dependence exists, is that we have to compute these bases in different regions of our parametric space. And there's different ways that people approach this problem. Different groups or different works in the literature approach the problem. One of the more popular ones is to create clusters in the parametric space and just compute this basis for snapshots within that cluster. What is not so nice about this approach, or at least bothered me, was the fact that it's not a smooth dependence relationship. So in an effort to develop something like this, we have proposed this coefficient matrix interpolation scheme, where the reduced order matrices are produced through a double projection. First, a projection to have the local basis, a second projection to extract a coefficient dependence of these local bases on a global basis coefficient, on a global basis matrix. And the connection between the two is actually enforced through an autoencoder. The tool that we used previously for reduction is now used for expressing this dependence relationship, giving us basis matrices by inputting specific sets of our parametric space. What does this mean? So given the problem of our frame, for different parameters of the load of the earthquake, but also different parameters of the configuration of the frame, we can produce, through this conditioning, this conditional variational autoencoder, the coefficient vector, which when multiplied with a global basis matrix that I can generate from my snapshots, my original simulations, will give me targeted local bases that will define the new reduced equation of the problem that I need to solve. And so this is the way in which we tackled this problem, which gave us really, at least for this kind of an application, an edge. We can compute with higher accuracy, but also quite interestingly, somehow accelerated computational time, but more importantly for us, we can also generate confidence intervals for our prediction. And what empowers us to produce these confidence intervals is the fact that we use a variational autoencoder, which is on its own a sampling approach. So our latent space is no longer a deterministic space, but it's actually a distribution, which allows us to generate samples that can then create this prediction, which is stochastic in nature, something that's important to give also a confidence in the prediction that we furnish, which is at the end of the day always an approximation. So this is our attempt to reduction, and now I would like to take a portion of the talk to discuss the connection with data in real time. So we know we can reduce our models, but how do we bring the data into play? And one way to do this, at least one way that we have long worked for in our group, is to do it through Bayesian filtering formulations. How does this work? Well, we still have this equation of the dynamics, which requires a model of the system, possibly a reduced order model, as I mentioned before. But we additionally have an observation equation. These are the few and sparse measurements that we extract from the system. It's not all degrees of freedom, but the ones that we have the luxury to instrument and draw information from. Now, the combination of the model and the data can be achieved by using a Bayesian logic, which is really a two-step logic. First, we predict the response of our system at the next point in time by using the equation of our system, which was essentially this state space formulation, even if it's a nonlinear state space formulation. And the second step is to update our estimation on the basis of the discrepancy between what we predict and what we measure at those sparse locations. And these are represented here through the likelihood and the prior, which are basically combined through the Bayesian logic to give us a posterior estimate of the response of the system at the next point in time, a posterior that is conditioned on the data that we collect, but also on the physics, which is imprinted on the models, on the equations that define the likelihood and the prior. So here's how this works. For nonlinear systems, it is not easy to use linear formulations like the Kalman filter for those who are familiar with these specific formulations. Instead, we have to relax a bit our simulation, and we use approximations that are based on samples. So assume you have a dynamic system at a given point in time. Its state, its response, is approximated with sampling, which tries to represent the probability that our system is at a given displacement and velocity configuration at that point in time. We have an equation, a state equation, usually, which can be a nonlinear reduced order model that can tell us what is the response of our system at the next point in time. This would be what we call our prior. And then we also have measurements, which can give us a sense of how far what we predict is from the reality. And this is then weighed in through Bayes' theorem to give us the posterior estimate of the response of the system. And all of this is achieved through the use of reduced order models. And because of this, it can be done in real time for different types of tasks of interest, including control and diagnostics. Now, in our group, we have worked for a long time, actually, essentially since the end of my PhD, on schemes that are using this Bayesian logic for state estimation, meaning the response of the system, joint state and parameter estimation, so we can also actually infer the parameters of the system when these are assumed as unknowns, or input state estimation, because I mentioned that the inputs and the loads are hardly ever precisely measured, so there is a way to use this framework to also assess the loads, or to assess everything everywhere all at once, which is everything, the input, the state, and the parameter of the system, of course, given specific properties are respected, because this can be a very ill-posed problem otherwise. So let me show you an example of how this can work. And to do this, I will use a simulated case study, which is from one of our projects that was on aerospace structures. And there, the idea was to use a few sensors that could be mounted, for example, on the fuselage, and understand what is the response of the system, first of all, in unmeasured locations, so that we get a full field image of how the structure response, but to also possibly detect the presence of faults and defects in these thin shell structures, usually come in the form of cracking, which could be in multiple locations. And so to do this, we will use physics, and the physics we use in our group is an extended finite element approach, which is particularly suited for fracture, but is not real time. So we will have to also use the reduced order modeling approach that I mentioned before. But where a challenge exists in our bringing down the equations of the problem from this full dimension to a reduced dimension, because now, in order to extract these modes of the system, it is important for us to have a configuration of the system that remains the same under different parametric configurations. And here's the problem. When a parameter of the system is a crack, which can have different locations, if I am to use different meshes, or even the XFAM approach, which is particularly adept in keeping the same mesh but still adding degrees of freedom, suddenly, if the location of the crack changes, I would not be able to have the same type of reference for my system. I would not be able to produce modes that match or make sense. Because of these crack parameters, I would have a non-smooth problem, which, however, we tried to tackle by bringing back our knowledge from physics and mechanics. So we used a sort of trick. We used mesh morphing, where we take the original curved configuration. First, we map it into a flat mesh, and we assume that we have a reference crack somewhere located conveniently within the main body of the object, which we then distort. We basically distort the mesh using modified inverse distance weighting, which allows us to bring the original crack into a new location. So we can then represent a new crack within our space, but using the exact same nodes and the numbering remaining the same, which means that I can then also use this logic of reduction by referring to the same node numbers. And now I am able to use the reduced order model that I explained before to approximate the dynamic response of a cracked curved surface. And I can do it in real time, which is actually faster than this video, luckily for us. And this means that I can also feed the measurements that I have in the Bayesian logic that I showed before, together with this reduced model. And indeed, this is what we do. There is actually even a further step of complexity here, because the input in this kind of system is certainly not measured. So I have to operate with a filter that can tackle unknown inputs. This type of filter, there are many such filters. Here we use an augmented Kalman filter to do this. And in fact, we use a bank parallel installations of these filters so that we can actually at the same time infer not only the response of the system, but also the parameters of the system, which include the location of the crack, which is the defect we're trying to identify. This shows you the convergence of our algorithm as we start from random locations and assumptions of faults and their positions at time 0. And slowly, as the estimation progresses, we have a convergence to the true location of these faults. And quite importantly for us, we also have the possibility to estimate the response of the system in non-measured locations. These green locations are not sensed, so we can actually quite fairly, it's a simulated problem, so here maybe it's a bit easier, but we can show that we can reproduce the response of the system. And in fact, we can do it at a fraction of the time that is required, even by improved solvers and accelerated models. So 22 seconds would be the best case scenario for a FEM-based approach. 0.12 seconds is what the surrogate here can achieve. There is a further complexity here that I'm not going to go into details of, so I'd rather just keep this for later in case there is interest for this. It's how we would tackle further challenges relating to input. So let me see if I can skip this because it seems a bit stuck. There we go. So what I would like to discuss here, finally, is the aspect of model discrepancy. Because what I showed before actually is very nice, and I showed that it works well on simulated data, but what happens in real cases is that additional to uncertain inputs and uncertain parameters of our models, we also have model mismatch, what we call model form uncertainty. In other words, we can never promise that our physics is good enough to capture the full phenomenon of what we observe. And to tackle this, we have been working with our group in Singapore as well, but primarily with this group on the development of physics enhanced, as we call it, or physics infused learning. And we have been playing with schemes that are so-called physics guided schemes, where the physics comes through explicit incorporation of equations into the problem. Physics encoded schemes, where we try to force the neural network architecture to respect the physics of the problem. For example, we use neural ODEs to reflect systems that form ordinary differential equations, or physics-informed schemes where the infusion of the physics is a bit more loose, but it tries to bring in concepts like Hamiltonian principles, symplectic integration that would go well with those principles, or physics-informed neural networks, where again, in the likelihood function, we try to demand the satisfaction of specific governing equations. So we try to actually organize the different tools that exist in the spectrum, which reflects the use of physics versus the use of data. So the Bayesian filtering scheme that I mentioned earlier tends to use a lot of physics, but requires less data because it assumes a good knowledge of the physics that's underlying the problem. But as we go into more physics agnostic representations, we tend to rely more heavily on the data. Or we can try to merge the two into something that is a compromise. And that's what I would like to show here as a final application, an application which we use for drive-by monitoring. This is basically the assessment of traversed infrastructure, roads or railways by trains or cars, where the sensors are mounted on the vehicles, the collected information is vibration, and we try to assess the condition of the infrastructure itself. We do this by using these models that are in the in-between or gray zone of that spectrum, where we have some knowledge of the physics, but it's not perfect. And we add a learning model that is there to take on the portion of the physics that we simply do not know or is at least hidden to us. By superimposing these terms and learning a combination of the two, we're able to make up for this model form mismatch, but we're also able to bias what would have been a purely black box model by the partial physics that we know and which operates beneficially for our system. Here's a simple example. This is the case. Let me not go into the details of this, but let me rather show you this application. The simple example for the case of drive-by monitoring, where we're trying to understand the roughness of the road surface, and where we fuse a model of the vehicle, at least a partial model of the vehicle that tries to approximate it, plus a portion that is a learning term, a deep learning term that tries to make up for the unknown or the model form discrepancy. And there is actually a logic, a weighting factor that is the optimal combination of the two. This is actually not something that the user tunes. This is just forced here to show the point. It's something that is learned by the framework and that allows us to get the best of both worlds. We have actually also experimentally validated this logic. Because I'm close to the end, I will not show you the experimental validation. I will just like to go to this, sort of leave you with what I think is next after this kind of fusion, which is the last portion of the chain that I showed in the beginning. And that was about handling systems of systems. And here is such an example at the ecosystem level. Here we try to harness information for wind farms, but we're trying to do it in a way that can allow for transfer of knowledge. So we have models, first of all, of wind farm layouts, where we try to, which we try to approximate using a graph representation. We consider a graph representation as possibly the most comfortable representation for representing systems that have a geometric distribution. This is true not only for structures that admit a mesh, but also for wind turbines, which are individual entities distributed within a farm. And by training such graph neural network-based models, we're able to train on specific configurations on which we have data, or simulated but even real data, and then we try to simulate systems of new and unseen geometric configurations purely as forward simulations to produce quantities of interest. And we show that it is possible to produce indeed such quantities of interest, like the power produced, the turbulence intensity that is experienced, the damage equivalent load, on the basis of few inputs, like the mean wind field conditions in the farm, and training on different separate farm geometries. And the power of such a transfer lies in the exploitation of the principle of graphs. This is what we would like to use, therefore, for the so-called population-based SHM approach, where we don't just care about the individual structure, but the assembly of these structures. I would like to close with this. This is sort of a holistic view of the framework we would like to put in place, which takes us from exploitation of data, the fusion of this data with physics to extract hybrid models that are more informative, offer this information to the experts and stakeholders for decision support, and then augment this kind of management to the level of fleets and ecosystems of different types of structures. So I think this is a good slide to close, since I'm very close to the end of the seminar, and ask for any questions that you have on this sort of chain that I tried to explain.
Thank you so much. I mean, it sounds like you have a lot more to present, actually. It feels like we have to invite you one more time.
No, I think I tried to organize, I tried to skip a few just to make the point I wish to make, but I'm sorry. I think I took a bit more time than I planned, and I'm sorry for this.
Well,
but
no
hopefully
worries, no
it
worries.
gives an overview of what we have in store.
Yeah. I mean, we saw the snippets of a lot of stuff, but every single snippet was pretty interesting and exciting. I can see. I can see why you are so excited about your project. Just by listening to your talk. That was awesome. All right, let's have a Q&A session. If you have any questions, please, unmute yourself and ask questions. Yeah, go ahead.
Thanks. Hi, Eleni. Good to see you in this context.
Hi, I didn't recognize you. It's nice to see you.
I mean, it was very, very detailed presentation. I have a high-level question for you, because all of us throw the words digital twin around.
Yeah,
and if you were to define it yourself, what would you say it is?
Well, in the context of, a digital twin has come to grow into something that is exploited by many different disciplines. And in this sense, I think it can also have many different meanings. I mean, it's different for BIM, right? The building information modeling, maybe, where it's more of an instantiation of a system. For monitoring, however, it is extremely important for this twin to be interactive and continuously updated, which means we sort of have to have this closed loop, which allows us to always understand the condition of the system, and it makes it possible for us to intervene. And it's very similar in control. And I know that probably you share the opinion from your applications. If you wish to be able to interact with the system, it cannot be without having this constant supervision. So a twin for me is something that has a closed loop communication with the actual physical system. And that's not always the case. And maybe it's fine, but in our context, this is what it should be.
Yeah, that makes sense. I think context defines it, and everybody's stealing it for the purpose of marketing.
Yeah.
So
That's true. Indeed.
And I really like your last slide, and I will steal it. And then
sure,
it is a beautiful slide, but everything is connected. I think that's the essence of it. Thank you. Beautiful talk. Thank you.
Well, related to the beautiful slide, Eleni, would you mind sharing your slide?
Yeah. Let me do that again. I did it because I couldn't see the audience otherwise, but maybe I can. I have to do full screen. Is it visible now? Probably.
Yeah, awesome. Well, I see that not just the last slide, but I see many other slides were pretty beautiful.
Well, thank you for saying.
All right, sounds good. There's a question in chat room by Peter. Well, instead of me asking, maybe Peter, do you want to unmute yourself and ask that question yourself, or do you want me to read it for you?
Or I can try to read it, but I have to stop the screen share, I think, again.
Yeah, I can read it for you.
Okay.
Peter has a mic issue. Is the causal relationship between inputs and outputs of the interest always clear? Or do you sometimes have to perform additional data analysis to establish the causality prior to the development of a physical model?
Yeah, this is a very good question. Because as I mentioned at one point of the presentation, it's very easy to end up with an ill-posed problem when we claim that there are many things that we do not know, including the actual loading source of a dynamic system. When this is unknown, things become quite difficult. So there are some formal checks. When we try to impose a model structure, we should first check if our model is observable. We should check the detectability somehow of the system, which means that, which is always easier to do with linear systems, but you can also do with nonlinear systems. So this is an important check to try and do formally when you try to put a model into the loop. For purely data-driven representations, another check that has to be done, because oftentimes we try to extract a purely data-driven model, is the parsimony of the representation that we extract. So these checks are important and should be in place in order to have a representation that is really performant. Otherwise, it could be that you have overfitting, that you have non-convergence, that you have instability, and actually something that is not usable at the end of the day.
Totally agree. Some sort of pre-processing of the data and to make it, quality data. It's, I think
but even the model as well has to be checked, and it has to be something that is in a position to operate with the inputs that we have in hand.
Yeah.
Because here we're not, since our interest is to fuse some sort of model into the representation, it also has to be configured in an appropriate way.
Right. Yeah. So nothing is perfectly automatic. Some knowledge has to be injected. Peter also asked another question. Are there specific tools you use to establish this, like convergence?
Yes, the tools from the side of the models is more on observability, as I mentioned before, is the parsimony of these models. But then when you're talking about data, it is indeed aspects that have to do with the correlations of the driving inputs and different checks that could guarantee the sufficiency somehow of the data. For describing the problem at hand. There's also tests that we do to understand how linear or nonlinear problem is. For example, through using coherence functions or other types of input-output relationship checks or statistical checks, and
awesome.
That define the nature of the problem.
All right, thank you, Eleni. Is there any other question? Please unmute and ask your question. Well, I mean, I have many questions, but respecting the time, I guess I can email you separately.
Yes, that would also be welcome.
Maybe
I can show my email there I think I may have it on one of our last slides. So this is an image of our group. It also contains my email where you can reach me with any comments, feedback, or also intentions for collaboration. That would be very welcome.
Awesome,
it's one of the nice outcomes of such talks. So
exactly. And I do myself see that there are a couple of topics we can collaborate. So I'm very excited.
Yeah, that would be awesome. I'll wait to hear from you and from others who may be interested in that case. Yeah,
definitely. You will hear from us for sure. All right. With that, I guess we can, thank our speaker for the wonderful talk and interesting presentations. And thank you so much, Eleni.
No, thank you. It was my pleasure. So I hope to get to see you again soon.
Yeah. Thank you so much.
Have a nice day.